Okay, good. I give you a couple of minutes to do that. See, nobody's talking to me. Kristen, Jonathan, Sawan, Shandon. Anyway, so I don't know if I'm talking, if anybody's there, but let me just do it. The V coil, the I coil in Y series. In Y series, I coil equals I phase equals I line. Okay. In other words, where does this current here come from? This comes from right here. This comes from the phase. That's I phase. And where does I phase come from? I phase comes from right here. That's I line. So the line current goes straight down into the coil. So the three of them are the same. So the answer for I line is 411.2814 amps. That's the answer for that. Okay. Then when you get to the voltage, this is V coil here. This is V coil. This is V coil. And the two of them together will make up V phase. This is V phase. So V phase equals 2 times V coil. So this is equal to 2 times a 277.1281. So V phase would be equal to whatever that comes to. It's going to be 277.1281 times 2. 554.2562. 0.2562 volts. That's V phase right there. Okay. And V line, this is a 3-phase Y, V line is equal to √3 times V phase. So this is equal to √3 times 554.2562. So V line, which is the maximum supply line voltage, would be equal to that times √3, which is 959.9999. 959.4999 volts. Voltage, whoops. Yeah. So that's the that would be that's the maximum voltage right there. That's what you get as the maximum voltage. Because this is going to be the coil value, and double that to get the phase value, and then multiply by 3 to get the line value. So that'll be the maximum line value. And if you want to check the power, you could go ahead and multiply that, and we should get the same. Should get the same power. Let's check it. Let's go HP. Let's go horsepower. Wait, don't put HP. Let's go back to blue. So let's go HP equals √3 times 411 0.2814 times 959.9999 times 0.83 times 0.92 over 746. Okay, so let's multiply that out. Let's say 411.2814 times 959.1244 times 0.83 times 0.2 times root 3 divided by 746. And that gives, what can I get 600 something? What's that? Get 600, wait a minute, 600, we should get the same power. 277. Oh, I'm using the wrong coil current. Let's see what it, I think this, yeah, I think I can see where I went wrong. I might have gone wrong here. You see? Yeah. Let's see. This current here is the main. Is the main current here. I didn't divide it by 2. That's what. That's okay. Yeah, that's what I did. This right here is 411.2814. But I need to find the current here, which is half of that current. That's my mistake right there. Yes. Okay, 411.2814 divided by 2. Yes. Right. So this current here is, this is the main current. This is I. Get I club. This shows it has to be divided by 2. So I coil equals 205.647 amps. Yeah, because this is the main line current, but the coil current will be here. So I need all the coil information. So that should be that. Did I use that over here? No. So this up here needs to be changed. So this right here is 205.647 amps. Therefore, this current here should be 205.647. 205. Okay, so let's, all right, so let's do that. So let's get 205.647 times 959.1 times 0.83 times 0.92 times root 3 divided by 746. Yes. Perfect. Bloody genius. Look at that. 349.9999 horsepower. Which is the rated horsepower. So this machine at this current and this maximum voltage develops the same horsepower. Yes, that's how you do it. Now let's do the minimum voltage is delta. Draw that in green. It would be delta. The minimum voltage would be delta parallel. So let's do here. Let's go here. Let's do minimum voltage. Minimum voltage always occurs in delta parallel. So let's draw a circuit for delta parallel, which will be here. Break this up into parallel. 1, 2, 3, 4. 1, 2, 3, 4. So go here. Go down a bit more, and then let's put more plus here and go up here. And do 1, 2, 3. Okay, so bring this up here some more. So come from over here, and come from over here, and come from and then we're gonna get here. This is gonna be VL here. And this is gonna be IL here. Okay. Now if you look at right here, this right here is V coil. But in this particular diagram, V coil equals V phase, which is equal to V line. All of them equal the same thing. Therefore, this is equal to 277.1281 volts. So that would be the line voltage there. That would be V line. That's the minimum voltage right there. Okay, and now you have to find the line current. Well, we know the coil current, which is this current. Let's change color. Let's go to black. This current right here, this is the coil current. This is I coil, which is this value here. Excuse me. This is 205.647 amps. See? And then this is the same current here. This is I coil. So if both of these currents are the same and I add them together, I will get this current here, which is I phase. And if I have the phase current, I can multiply by root 3 and get the line current. So what I got to do first then is I have to say I phase is equal to 2 times 205.6407. And that's equal to, let me do that, 205.6407 times 2. That's 411. Oh, that's the opposite of that. That's 411. Oops. That is 411.2814. Then we could find the line current. I line would be root 3 times 411.2814, which is equal to times second root 3 equals 712. 712.3603. 3603 amps. That is that. Okay. So let's make sure. Once I calculate the power, I'll be able to tell if there's any problem. So let's get to the power. Plus power is equal to root 3 712.3603 times the voltage, which is 277. 277.1281. 1281 times the power factor times the efficiency divided by 746. Now, if this works out, we good. That means everything was correct. So let's go cross your fingers and let's see. 712.3603 times 277.1281 times 0.83 times 0.92 times root 3 equals that divided by 746. Perfect. Yes. 349.999. Yes. Yes, man. I know what I'm doing. Boom. Same answer, the 350 in the original problem. In the original problem, you know that the power is right here, 350, and all of these come out to have same power. So you know that they match up. So when I did the minimum voltage, it came to when I did the minimum, it came to 349, which is 350. When I did the maximum, it came to 349, which is 350. So that means these values are, let me put them in red. So the maximum value that you could use in this system would be 959, 960 volts, and the current it will draw at that time would be 205 6407. That's the maximum voltage and the corresponding current. And then the minimum voltage would be this right here. Oops. Would be the 277. It's the minimum voltage. And then the current at that time, the corresponding current would be 712. Okay. Now, if you would notice something, which you would notice is when the voltage goes down to this minimum, the current comes up to a maximum current. This is the maximum current. At the time when the minimum voltage occurs, the maximum current occurs, and vice versa. And right here, if we go right here, as this voltage goes up to the highest voltage, notice the current. The current goes down to the minimum current. As the voltage goes up to a maximum of 960, the smallest current in the whole system is 205.6407, goes to minimum. So the minimum current occurs at the maximum voltage, and the maximum current occurs at the minimum voltage. That's how the system works. And it should make sense to you because you know that P is equal to IV. If P is a constant and V goes up, the only way to maintain the constant is for I to come down. And the converse of that is if P is equal to IV and V goes down, in order for that product to still equal to P, the same P, which is that same P, this current here must go up. You see, that's simple, basic mathematics. You know, for a product to maintain, the one part goes up, the other part must come down. All right, so that's it. Any questions there? That's the finish with the motor problem. So we can go on to the transformer. Any questions there, anybody on that? So you should know how to do that. So if I give you a whole one to do from scratch, so like if I give you one of these for your final, you should be able to work it out once you know all of that. That's the minimum voltage. And the part 6, we already did that. I don't have to do that because we did that a couple of times. To find we did that extensively. Find the different, when all the coils are healthy, find the ohms, and when one is shorted and when one is open. And I even did it when there were 2 shorted and 2 open. So you should know that pretty good. All right, any questions, anybody on that? You got on that? I see Bruce asked me about it, but Bruce ain't even in here. Bruce gone. I don't know if something happened. But Bruce looked like he's skedaddled. I don't know if he's had electrical problems or internet problems. All right, so any questions? Shandon, Sarwan, Jonathan, Christian, and Kriston.
No, I'm good.
Good. All right, good. All right, so make sure you can do that practice. And we'll go on Tuesday, we're going to go on to this. I can show you the problem. It's right here. We're going to go on to this problem right here. An electrical engineering plant, which is capable of supplying an industrial park with electrical energy, is located at such a distance from the park to warrant using a high voltage system to be economical. Some information with regard to the system listed below. The plant, generating plant voltage 7 kilovolts, step up delta Y transformer, turns ratio of 15 to 300, and with a maximum power rating of 5 megavolt amps. Industrial park substation, the bus bar voltage is 416. It has 2 parallel connected step down delta Y transformers. And so from all that information, you have to find out what's the high tension voltage, that's the transmission voltage, and what is the transmission current. And then find the turns ratio of the substation of the load on the load side, that's at the park. And then the maximum power the park could draw if the power factor is 0.81, and give your answer in megawatts. And then the minimum load of the park substation transformer, if each is capable of carrying 80%, and then not to be loaded to more than 80%. So this is basically the information you would need if you were going to purchase a transformer. Okay, they need to be able to carry 80% of the load, and when they're carrying 80% of the load, they don't need to be loaded to more than 8% of their full capacity. That's what this question is asking you. What is that capacity? And then this is here's asking you about what we call taps. You can put taps on a transformer, taps on the primary, taps on the secondary. So this one here says if the number of turns on the primary winding of the substation step down transformer is 4,000, to how many turns must it be changed? Must the primary winding be changed in order to counteract a voltage drop of 6%, which may occur between the terminals of the transformers at the back substation? So in other words, you're saying there's a voltage drop on the system. Like when you load down the system, like the way systems work, the way all electronic things work and power things work, you could work them out on paper, you can build them, and you could calculate exactly what they will do. But what they will do is different, will still be different from what you calculate. So even though we think we understand them and we got everything covered, we still can predict 100% what they will do when there's load there. Because the loads, when you have a community, the loads are so very, I don't know if variant, I don't know if that's the proper word, but the loads can be any kind of loads, they can be capacitive, inductive, resistive, and any combination thereof. But in any event, once you connect up a system, that system is gonna the load on that system is gonna reduce the power system. Don't care how much you try to regulate that, that's gonna drop down some. And so therefore you have to have some kind of possibility to counteract the drop. And so this is what this question is asking you. One method of counteracting the drop is to put taps on this transformer, on the secondary or the primary. This transformer here is asking you to change the primary windings. Therefore, there are taps on the primary side. Okay? And so basically it's asking you to do this. When there's a 6% drop on the secondary, that's a reduction in voltage. If I make the transformer step up more, then that means I can handle the drop. I'm not getting rid of the drop. It's just that I made the voltage higher. So when the drop occurs, it drops down to the voltage that I'm supposed to be at. And when you change the taps on the primary, as you make the taps on the primary lower, you convert the transformer to a more of a greater step up transformer. Every time you reduce the turns, you reduce the primary in comparison to secondary, the transformer steps up more. That's how power systems work. That's how BC makes the voltage higher or lower. You go up on the primary, you decrease the output voltage of the secondary. You go down on the primary windings, you increase the output on the secondary voltage. So that's it. So we're going to do that on Tuesday. All right. So that's it. That's my spiel. Any questions?